people get their pizza. So welcome to the first talk of the semester's Tools and Technology Seminar Series. Hopefully you saw in the latest email I sent out, we did add a talk for the first Thursday in May, so we are going to go through first Thursday in May as of right now. So I'll make sure everyone's aware of that. I think most of you have all been here before, so you're familiar with the seminar series, but since this is the first one of the semester, I'll just give a brief introduction. It's basically just a venue to talk about tools, technologies, methodologies. They can be currently in development, so it doesn't have to be a final product. It could be something that you've used for a long time, but maybe you're using it in an innovative or novel way, or it's just of interest to researchers. Yeah, so today's speaker, I'd like to introduce Adrian Tan from Biostatistics, I believe, and he's going to talk to us about VT. There is a sign-in sheet hopefully going around. Please sign it.
Thank you, Marcy. So again, I'm Adrian, and I'm a PhD student from the Department of Biostats in the School of Public Health. I'm working on genetic variant calling on next generation sequencing data, and I work for, my supervisor is Hyun Kang. Just to get a rough idea, may I know if there's anyone here who's working on variant calling? Or what kind of variants are you guys working on?
I did looking through RNA-seq data in head and neck cancer.
So SNPs and...
There are SNPs and small indels.
Okay. Anyone else works with indels or short tandem repeats? Not really. Okay. I assume that most of you use VCF files and BCF files. Okay. I wasn't too sure about the audience, so I tried to structure a talk such that it might be relevant to you guys, but I'll just jump to it a little bit first. Okay, so VT is actually a suite of tools written by me for most of my dissertation work. And it consists of three major portions: variant calling itself, variant analysis, evaluating the set of variants you should get from it, and VCF and BCF manipulation. So together, these three allows me to make a pipeline to do the evaluation and do all the analysis such that it is accessible to people. It's actually available on GitHub. So it's more about in terms of reproducible research too. Okay, so so the focus today, I'll be talking about first something called the unified representation of variance, which is actually an aspect of variant calling itself. Because when you're calling a variant, you have to represent it, and it has to be in a consistent fashion. Another part which I'm going to talk about is about variable number of tandem repeat detection, which also includes short tandem repeats. Okay, and also some useful tips for dealing with VCFs and BCFs using VT itself. Okay. So first part here, the unified representation of genetic variants. This was published last year, and the problem is actually this. Okay, a variant in the VCF file can be represented in many different ways. So this is actually the reference sequence. Okay, and this is the alternate sequence. Okay, so the variant is basically a CA deletion. Okay, when you present it in a variant call format, okay, you can actually have multiple representations given by this 4 here, where the positions are at 6, 3, 2, 3, and they have different length in the representation of it. And mind you, this is all looking at the same variant. Okay, so it's an important issue when you study variants, because if you look at it and you don't really make sure that you're clear about it, you might be studying 4 variants which are actually the same thing. So that is an issue. Okay. So what we want to do here, right, is to be able to represent it in a consistent fashion, and we call this variant normalization. So this problem was actually presented to me like around, I think, 3 years ago when I was working in a 1,000 genomes project. We were comparing the variant call sets of like 8 or 9 callers. And the problem is that amongst the indels, there was lots of discordance. And to a certain extent, the discordance is due to representation. So we sat down and tried to figure out, so how do we want to represent in a consistent fashion? So we want to talk about it. Okay, we want it to be parsimonious in length. That's one requirement. And another thing is left alignment. Okay, so left alignment is something which I think is actually kind of introduced by the people in the 1,000 genomes. I think people who are working with the HGVS representation, they use right alignment instead. Okay, I think some of you guys will have that. Okay, but the thing is that with these two ideas, right, it's not really easy to translate into the sequence. So what makes it parsimonious and what is left aligned? So if we were to look at it carefully and we work it out, and it could be worked out mathematically, we can actually show that the corollary of this is that a variant is normalized if and only if these two conditions are met. The first one is that the alleles end with at least two different nucleotides, and that the alleles start with at least two different nucleotides, or the shortest allele has length 1. It's just a very, very simple rule, and this really helped things a lot. So when I was working on this originally, we actually tried lots of different solutions, and looking at what other people did, they actually use another hidden Markov model or aligner to realign it with different scores just to left align things. But apparently you don't actually need that. You can just do it with a simple algorithm to make sure that these properties are actually satisfied. Okay, so let's look at the 4 variants which we had earlier, and based on those 2 rules that we have, right, I want to classify what's wrong with each of them. So for the first one is at position 6, okay, and the alleles, right, end with the same base, C and C at the end. So this means it is not left aligned. Very simple rules, okay. And then the second one, again, there's A and A at the end. That means it's not left aligned. And in this case, it's also not parsimonious because you can just truncate both the 2 A's, CA's at the end to make it shorter, okay. The third one is just not parsimonious because there's an extra G on the left side, okay. And then finally, the last one satisfies both properties, where the end bases are not the same, A and G, and that the front bases is one of them has length 1, which is G here, even though they are both the same. So this satisfies those 2 properties, and that gives you a normalized variant. So this can also be proved to be a unique representation. And if you look through the paper, you can see the mathematical details for it. Okay, it's a simple thing with a really, okay, sorry, I need to show you this first. So the variant normalization algorithm is just this. We just apply this algorithm. If all the alleles end the same nucleotide, then truncate the rightmost. And if any allele is length 0, then you extend all alleles by 1 nucleotide to the left. So this portion here does what we call right trimming of the allele, of the variant, and left aligning at the same time. And then after that is done, okay, we do left trimming if necessary. Okay, so the algorithm turns out to be something really simple to solve a problem which no one was able to define previously, and that's why we have this. This stuff was actually on the wiki page from our genome wiki since I think 2013. So we only just published it recently, mostly because people wanted it. Okay, so this is an impact of what normalization causes on public resources. So let me focus on the first column first. So before normalization, you have 9,996 indels here. This indel array is actually from a data set from Dr. Ryan Mills. I think he wrote it in 2011. They chose, I think, 10,000 or so indels to analyze from the original set. And they actually, so the one which I had was a slight subset of it, 9,996. So it turns out, right, that after normalization, actually there are 8,904. Okay, most of them were not left aligned, and this second row here shows you the overlap with the 1,000 genome indels. So if I did not normalize it, only 49% of them overlap with it. But when you normalize it, 80% overlap with it. Okay, and then out of all the 9,996, 40% of them need normalization. And after normalization, you realize that 11% of them are actually representing the same indels. So yeah, these are the kind of things which we need to resolve when you study indels and make those changes here. So I think to date, I think most scholars still don't really do it completely properly, like platypus and freebase. So you still have to apply this. Okay. And another example for public resource is the dbSNP 141 VCF file, which you can find online. And it turns out that 14% of them needed normalization, and that 4.6% of them were actually done. Okay. So if you look at in terms of pure numbers, it's around 300,000 indels. So this is the end of it. Okay, so implementation-wise, it's actually found in VT normalize. So VT actually has the program, right? It's called VT, but it has a lot of subcommands like normalize. I'll show you the wiki page later and talk more about it. BCF tools have also implemented our algorithm, so you can also use it from BCF tools. It's called norm, and this tool has been used in quite a few other pipelines out there. Okay. It's used in Gemini. It's an online tool for variant querying and data exploration. And some variant calling pipeline used in Harvard called BC Bio Next Gen, and also a pipeline which is called GKNO is in Utah from UStar. Okay. So if you're working with indels, please have a look at this just to make sure that you're working with indels in the correct fashion. Okay. So next to the second part of the talk, okay, I want to talk about the detection of variable number of tandem repeats. Okay, but before we start, I'll just warm you up. Why is this of interest when we're working with this? So usually when we're talking about genetic variants, which we discover from next generation sequencing data, we'll be looking, of course, at SNPs, which is the most common, and indels, the short ones, which are the second most common set of variants, and structural variants. We'll focus on the first two categories for the next few slides. Okay, one thing which I want to state here first, right? Okay, this is a finding which which was discovered by Hingley, I think 1 year or so ago, is that indels are highly enriched in repeat-rich regions. So, do you know what are the nature of these indels? They're all, a lot of them are actually short tandem repeats, and I'll give you some evidence here. Okay, so these repeat-rich regions, right, are defined, right, by short tandem repeats discovered by the tandem repeat finder. Okay, that's around 1.52% of the genome. And another program called MDAS, which is used in the NCBI pipeline to mask out low complexity regions, which also consists around 2.17% of the genome. And combine them is around 2.3. So this 2.3% of the genome is is mostly repetitious. And this is based on GRCH37. And the percentage of SNPs and indels in repeat-rich regions is shown in this table. So this is the 1,000 genomes phase 3 course set, which is unfiltered. And when you look at the SNPs, okay, there are 162 million of them, and 4% of them lie in the repeat-rich region, and 96% of them lie in the non-repeat-rich region. What is stark about this, right, is that for indels, the numbers are actually 66% versus 34%. So indels are highly enriched in repeat-rich regions. Okay, and yeah, is there a question?
The so-called highly enriched region is actually because when you have different samples using different sequencing and assembly, even if they have the same repeats, you assemble it in a different way, and so it's resizing.
Correct. I'll talk more about that shortly. So that's the point which I'm trying to bring up next. Okay, and that's why we want to handle it in a proper way. Okay, SNPs is not such a big issue. We notice it's around the same proportion. Okay, so anyway, the next step is that for the filtered data, okay, for SNPs, right, is 2% and 98%, which is proportional to the repeat-rich regions in the genome. But when you look at indels, it's 25% and 75%. So one thing which you'll notice from here, right, is that they've also kind of over-filtered the short tandem repeats from these regions. Yeah, and this is an issue. Okay, so this is the impact of it on concordance between call sets. So it's slightly involved this slide, but I'll start to go through it. Okay, so the left side here is the Venn diagram for a repeat-rich region. Okay, and this is for SNPs. Okay, and I compared it between three callers. One is haplotype caller, SAM2s, and platypus. Okay, the SNPs here, right, form 6.7% of these three call sets. Okay, and the concordance in a sense, right, is represented by hold on. Okay, it's around 46% overall. Okay. On the other hand, when you look at the non-repeat-rich region, I'll use this. Okay, when you look at the non-repeat rich region, okay, the concordance rate amongst all three call sets is 99%. So this is for SNPs. Okay, it's not such a big problem for SNPs because only 6.7% of them cause all these issues. So this is not the big problem. Okay. Oh yeah, these call sets were actually produced on NA12878 PCR-free data. Okay, high coverage. Okay. And this was actually reported by Hingley in 2014. And I'm reproducing the graph from another set on a different data set with different callers. Okay. So the next one which we're going to look at will be the indel call sets. So again, you see a similar thing that there's very low concordance here for the repeat rich region. And similarly, it's better in the non-repeat rich region, but it's still an issue, okay, between these three call sets. So over here, it's also related to the way they actually reassemble the reads, because haplotype caller and platypus reassemble the reads in a slightly different way. And SAM2 is the one which base it totally on alignment. Okay, but the key thing to note here is this proportion here is that the indels in this repeat rich region is around 66%, which causes all this discordance. So another way of looking at it is that most of the discordance between call sets are all, again, caused by this repeat rich region issues. Okay. Okay. So I'm going to explain what he tried to mention just now, actually. Okay. Is that one of the problems, right, is that this tandem repeats, right, can actually induce errors. So example of this, right, is this. This is an exact tandem repeat. Okay, it's exact because the copies are all replicated in exact fashion. So there are a fixed number of ACs. Okay, and the position of this is at 7, and its TAC is a deletion of 1 AC copy. Okay, and inexact tandem repeat will be the case where, let's say, the alternate sequence has a different base here. So this might be due to sequencing error, or it can be a real mutation of some sort. Okay, and when you have this, okay, suddenly the representation in VCF, right, even when it's normalized, is now at position 19. Okay, with the reference as CAC, deletion of AC replaced by a G. Okay, and then we have another one where, let's say, the reference itself has a bit of noise there, so they replace the C with G, and then again you get a different position. Okay, so when you look at it as a whole thing, right, is that when you're interested in a variant, you want to have a variant which you are able to assay consistently from different individuals. So they should be defined by the flanks, okay, instead of this little bit of noise. And these are things which cause the discordance between indels because they are actually tandem repeats. Okay, so the question is there an ideal way to actually represent this in exact VNTR? So we have a suggestion here is that instead of focusing too much on the little pieces here, we should actually treat it as a tandem repeat. Okay, and then just represent it as such. So they all have a consistent representation in this fashion. And this is actually done so far for tandem repeat callers. Except for tandem repeat callers, they don't really care about the evidence which is actually shown. And they like lobster or repeat sig, right? These are the main next gen sequencing, variant calling for tandem repeat programs. What they do is that they'll take the reference sequence and then they'll discover the repeats there, and then they only genotype those which are discovered within the reference. They don't actually use next gen sequencing data evidence in a sense. Okay, so okay, this is that. So okay, so this is another plot which kind of shows the repeat rich region being a factor in indels. So the y-axis shows is actually a histogram, is the count, the frequency of variance. The x-axis represents the length of the indel. So positive numbers for insertions, negative numbers for deletions. So the blue line represents indels in the non-repeat rich region, and the red one shows the indels in the repeat rich region. Okay, and you'll notice the key thing here is that the red line has a lot of spikes. Okay, and if you look more closely, they're at the even number, like 2, 4, 6, 8, these positions. This is actually thanks to repeat units, right, which are like AC, just two motives, two length long, two bases long. So that's an indicator of it. But if you look at the blue one, there are also some kinks here. So even for the non-repeat wish region, there are actually kind of like these repeats hanging around there. So something which you'll see in many call sets, and this is how it's being explained actually. Okay. So okay. Okay. So now we go to the next step is that we need to find a way, right, to do variable number of tandem repeat detection, not just on the sequence data, but on the indels you should actually get from there. So the key thing about this is that the input here is actually not the reference sequence straight away. It's actually the VCF files with the indels which you get from next-gen sequencing, and then you try and figure out what is the tandem repeat which is associated with it. So again, let's break down the makeup of a tandem repeat. And a tandem repeat will have a repeat track, and it also have a left flank and a right flank. They have a repeat unit of AC in this case, and in this case, this is the deleted sequence of this. So the key thing here to figure out what is a VNTR is actually simply a problem of detecting the flanks. Okay, and this will actually be a bit noisier, right, and messier when the repeat track has some noise in it, and we have ways to go around it. But we'll first talk about the easy one where it's exact. So to detect exact VNTR, we just need to get the candidate variance from aligned bands in the VCF file, okay, and then we do left and right alignment on it. So this is actually based on the algorithm which I described earlier for normalization, where you have left alignment. If they are both the same at the end, you just move one step to the left. So you can do the same thing for right. If it's on the right, there are two bases the same on the left, you just move one step to the right. Okay. And after you get the left and right alignment, right, you've gotten the repeat track, because I'm assuming it's exact, so you'll definitely get the full track. Okay. And you don't actually, well, okay, one interesting thing here is that you do not need to know the motive. You do not need to know how the motive looks like. Okay. After you do alignment and you detect the repeat track, then you detect the repeat unit. It must work because it is exact. Okay. And this is how it works. Okay, is that you have reference sequence and alternate sequence. I've highlighted the flanks and the variable portion. And if I do a left alignment, I'll shift the entire thing over here and I'll detect the sorry. So when you're left aligning or right aligning, you're actually aligning the gaps. So when you align the gaps to the left, you're detecting the flanks on the left first. And then when you do the right alignment, you're moving the gaps to the right, and you're detecting the flanks here. And voila, you get the repeat track, and of course, the flanks at the same time. And then once you have this right, okay, the repeat track, okay, we use a repeat tree. But there's actually a prefix tree, which I'm not going to describe here. It takes a bit of time to describe. And you can use that to actually figure out what is the most common motive here. Okay? Yeah. So very simple for exact VNTRs. That's how it works. Okay. The problem, right, is when it comes to inexact VNTRs, right, is that how do you do it? We'll get stuck if there's a bit of noise there. So we do the first three steps again, okay, but we'll add an additional fourth step, is that we allow for fuzzy left and right alignment, which allows for noise, okay, to obtain the flanks. And then we repeat steps 3 and 4 if the purity of the repeat track sequence is low, okay. And to do this, we actually worked out a hidden Markov model. We call it a repeat aware hidden Markov model. Okay, and we actually extended it from the description of a local hidden Markov model described in the book Biological Sequence Analysis. It's written by Richard Durbin et al. In 1998. So this is the graphical representation of it, and this is the model with the flanks and the repeat unit and the right flank. So in a way, you can treat it as it is some sort of like a regular, it's a robust regular expression in a sense. Okay, and we, of course, this is the full model. We actually modify it such that it can be used in multiple ways to detect the flanks. So how does this work? Okay, so we have the first step again. We have the left and right alignment. Okay, but unfortunately, because of this little change here, the G here, okay, that's an addition of a G. Okay, we only extract a little portion of the repeat track, which is AT here. Okay, assuming that we did manage to get the basic motive, okay, which we'll actually figure out then. Okay, we'll try and do a fuzzy left alignment. So this is how it works. Again, we look at the two sequences again. Okay, and this time we say that, okay, based on what we found earlier, we'll set this portion temporarily as the right flank, and then based on the AT motive which we detected earlier, we'll try and align this with this sequence. And then the alignment will be like this, where there's a full match here, and then it will generate the robust left alignment here with the repeats. And then this part here is unaligned. So this ends up giving our right flank, our left flank actually, sorry. Okay. And then we use that left flank again to put in another model here and generate the AT copies again. And then we get this alignment here, and then we get back the right flank. And so when you put all this together, we get the two flanks and repeat track. Okay, so this is how the model works. Okay, and it doesn't work perfectly all the time, in particular for cases where it's actually not a tandem repeat. So an issue about this is that we are applying to all the indels. Not all of them are tandem repeats, so not all of them will work. But that's what we want to do, in a sense that we want to figure out what is not exactly a tandem repeat and what is a simple indel. There's actually a lot of noise in between. It's actually a spectrum. So when you look at tandem repeats from like repeat finder, everything, they're actually very nice looking. It's pretty pure. Okay, but there are actually a lot of indels, right, where it's a big mess there, and it's actually filtered out by tandem repeat finder and lobster. But we can't get around this when we're working with the indels itself here. So one of the issues we actually have now is being able to systematically classify this spectrum. Okay, but this is one of the steps that allows us to move in that direction. Okay, so the impact of having this VNTR, this tandem repeat representation, is that, let's say we have two call sets between PL, platypus, and VT. Okay, by raw calls, right? Okay, in the repeat rich region, the concordance is just 55.9%. When we normalize it, it goes up to 60.2%. But when we go to the tandem repeat representation, it goes up to 75%. Okay, so that's how it improves the thing. So a lot of the discordance you see right now among callers, which people keep trying to solve, it's like you have to realize that there's actually no solution for something which is intractable. So you want to find a different way of representing it to make it consistent. And you really want to do that also because when you're studying genetic variance, you're not interested most of the time to just study one individual by itself. You want to study a population. So you want to find a systematic way to be able to get that information from many individuals. So you always to find the lowest common denominator, which makes it the same. Okay, so the definition of variant itself is what is different from the reference. So we should be thinking in terms of getting the right flanks rather than just picking up every indel which you see. So this is what we were trying to solve. It's solved to a certain extent, but we need to be able to figure out the spectrum on how to actually present it in a systematic fashion. Okay, so this is that. Okay, some other results is that an interesting thing is that for VNTRs, right, there are actually some things which overlap with VNTRs. Okay, and over there, right, we have something called the TSTV ratio. This is transition versus transversion. So usually, right, a good call set, right, we have a transversion, this ratio of around 2.1, 2.2 or more. Okay, and we'll find that SNPs actually have a pretty low TSTV when it's overlapping with VNTRs, and a high one when it's not overlapping with VNTRs, which kind of suggests that being able to detect these VNTRs also helps improve your SNP calls, because this might be something which you don't really want. You would want SNPs that you cannot consistently genotype across individuals. Okay. And finally, because we work with the indels directly itself, lobster actually depends only on short tandem repeats of length 6 and below. We actually detect more than that. So this is some value in being able to process the indels after, instead of depending strictly on a reference set of indels. Tandem repeats. Okay. Okay, this is implemented in the program Annotate Indels. You can see this in the wiki later. I'll show it a little bit. Actually, I can show it to you now. Hold on. Okay. So this annotate indels. So when you run this, okay, these are the indels which you observe in the call set. This is the indels. These are the tandem repeats which gets extracted using the algorithm. And then it actually has more information here on what is the motive, the repeat unit, the concordance values, and whatnot. Okay, so this is a perfect one. So that was an easy one to detect. There's one which is a poly T, but with two C's in between there. Okay, so it was detected in this fashion. Okay, yeah. So this is an example of the output. And this actually shows also the trace of the algorithm. Okay, when you and when you extract the candidate repeat track first, then you use the prefix tree to detect which are the possible repeat units. So it goes through a whole list of things, candidate motives, and then it does the left and right fuzzy alignment. Okay, which you can see here. The alignments are all done here, and then finally it outputs the actual repeat track. So you see over here, there's also a noise, one extra C here. So I think the proportion of this, right, reported by Lobster is around 50% of all tandem repeats will tend to have a little bit of noise in it. But I think we're finding quite a bit more actually. Okay, so that's that. Okay. So now to the third part of the talk. Okay, manipulation and analysis of variance. Okay, so a quick question here. So how many of you use VCF files here? See most of you. Do any of you use BCF files? Not one. Okay. So so BCF file is actually the binary version of VCF. Not many people use it now, as you can see. But I would like to try and get you people to start considering using it because it actually helps speed up your analysis and your tools when you write with it. Okay. So the main thing here is this. Okay. The BCF file, right, is a binary representation of VCF files. That means like if you have a float in it, it's actually represented in the computer like 32-bit version of that number. So you don't actually have to parse it. The parsing itself actually takes up a lot of time. In general, the compression between BCF and VCF is that if your data fields are rich, right, okay, BCF is actually bigger than VCF.gzip, okay? That's something which I don't think they talk much about, but that's the truth of it. This has to do, I think, with the fact that the binary files don't really compress that well on the gzip library, actually. But if you only have genotype data, right, BCF tends to be smaller by around 5 to 10%, okay? And again, the biggest thing which you have to be aware of, right, is that now we're working with like, I think 10,000 individuals for next generation sequencing, saving time like 40%, 50%, right, just due to the processing of parsing of all this text right into numbers, right, it takes up around a significant amount of time. And it's a smart thing probably to use BCF, and that's what I'll suggest here. So basically, it's just much faster for analysis. I use it all the time now actually. And your BCF records, you can also use it to stream records between programs. So when you pipe a program from one to another, you save a lot of time there. So those are the users you can think about because in view of the fact that we're going to get a lot more data and our clusters probably won't grow as fast in most cases. Okay, so one of the problems about this, right, okay, about why I think people don't use BCF files in the first place is that VCF files are actually more permissive. They allow for headers not to fully describe the fields. BCF requires all the fields to be described, and that, I guess, gives a little bit of impediment in people trying to move over BCF. And I don't think they realize how useful it is at this point in time. And usually, you have very large VCF files with incomplete headers. So for you to do that, you need to write up your VCF file again with the correct headers. So you have to reproduce the entire thing. Then you can convert it using something like BCF tools or VT. Okay. So we actually have a special mechanism in VT that helps go around this. Is that you can actually produce, and this is how it works. Okay. You extract the header, just the top part, and you just modify it such that it's complete. And then you rename it as the file, the name of the VCF file, header, and then you just convert it with VT view. Of course, you'll read that alternate header, so you don't have to rewrite the entire file again. So this is a useful little hack for you to move over BCF files easily. So the other thing is that actually reading the BCF files, right, okay, requires something called HTSLib. Okay, it's actually fairly mature now, and you can find it on GitHub. It's written by the folks in Sanger. Okay, and that will be a very useful library in C, right, for you to use to process this information. It takes a bit of time to get into it, but the savings are really huge. Okay. Okay. This mechanism is discussed in the wiki, so you can go there and check it out again. Okay, and another useful thing which I found for VT is that the sorting of chromosomes. So how many of you actually encountered this where people sort their chromosomes as 1, 10, 11 all the time, right? So this gives me an issue because in many cases I assume orderedness of variant files, and I process them in an ordered fashion. So if one of them is ordered, one of them is not ordered in this fashion, I'll lose a lot of overlap variants. So again, you want them to be listed and ordered according to the context listed in the header. So there's a little trick here for VT. I have a program which sorts it by chromosome based on the index. So that's a useful thing to do. Okay, and this again is described in the wiki. And it actually does a few extra things. Local sorting, the chromosome one which I just described, and a full sort, which you don't assume anything. The local sort occurs when the variant file is not sorted in only little stretches. So you don't want to resort everything, right? You just stream it and then you just sort locally within the window. So this is also a very fast solution for many things here. This is something which I encountered when we do normalization of variance, because when you left a line, then suddenly it goes out of order. So you use this little tool to sort everything. So this is something which is useful, which some of you might find. Okay, and another thing is that for VCF files, sometimes you want to know what's in it, especially when you get it from the new variant callers. And I have a tool called Peek. And what it does is that it summarizes all the variants, SNPs, MMPs, indels, and a whole bunch of others. I want to show you a little bit more on that. Oh, there. Okay. So this is a full list. It shows you all the genetic variants in all the different categories. There might be SNP indels, those that are next to each other, MMPs with indels, a mixture of these three where it's multi-allelic. Then it also looks through structural variants. So you can see all these things here, deletion, bar elements, everything. So this is actually the 1,000 genomes data release, which you can actually look at it. Okay, and then yeah, so this is what it can do. So okay. So another useful thing is the subsetting of variants. So I also implemented a whole bunch of filter expressions which I can apply to many VT tools. And the first expression says I want to have biallelic indels that are passed. Okay. The second one says that I want to have biallelic SNPs which are common because the allele frequency is greater than 0.5%, and indels that are rare, and that all of them must have a quality score of greater than 100. So this is actually really useful when I'm trying to look for problems in my call set, and you might find it useful too for you. Okay. And to use this right in many of the tools, like for example, like my view, you just use the -F option to put in the filter expression, and then you can get whatever you want. Okay. And this is described again in the header filters. Just have a look at it. I also do a lot of evaluation of my variants, which we do power analysis, which is comparison with known good data sets and comparisons with known bad data sets, which is the type 1 error analysis. And I have it implemented in a program called Profile Indels. There's a reference text to give you all the different reference data to check from, a data set which you want to compare against. Yeah. And this is how it looks. Here. Okay, so it gives you, for example, Okay, like you want to compare against DBSNP, so 34% of it overlaps with it. Then you have the Mills data set. Okay, and all this here gives you the insertion deletion ratios. Okay, and the frame shift, non-frame shift proportion and the ratio. And then this is the example of the reference file which contains all the information which you want. So all these files is also available in a resource bundle in VT, where you can just download it from the wiki page actually. So if you were to look at it, we have a resource bundle here under GRCH37. So these are all the reference files you can use. 1000 genomes, NA12878 from the Platinum data set, Janko annotations, Tandem repeats, yeah. Okay, and finally, yeah, a few more things. It also does Mandolin error analysis. So nowadays, this is actually a really, really powerful way of doing things. When you have experiments, it's always good to have families there, because this is actually independent of many other factors, and it's just a very, very useful tool which I found to be able to check for errors in your genotyping. Okay, so again, you can find it there, and okay, I think that's the end of the talk. Okay, so I'd like to thank my boss, Gonzalo, and Mike, and Ryan Mills for the work I've been doing here. So are there any questions? Yeah. I guess if there's no questions, we can go back to eating pizza. Okay.